We are starting a new chapter. It's actually 2 chapters in the textbook combined. It's chapters 11 and 20. They are separated in the textbook, but we like to put them together because they kind of flow into each other. For your purposes, you probably won't even know where that division happens, but it is actually 2 chapters. I'm going to share my screen. So I have updated the agenda. It probably will change a little bit because I'm not quite sure of the pacing. But for now, if you kind of want to have an idea of where we're going, the daily agenda is updated so you can go in and see what we're working on. So we're going to be starting with something called balancing chemical equations, or just balancing is what we call it. And we'll be probably doing that for 2 full days, possibly 3. And then we're going to move into reaction types from there. Also in Google Classroom, I have posted the slides and the packet. So if you do want to continue to take your notes virtually, they're in there. Okay, so chapter 11 and 20 is the current material. All right, so time to get started on the chapter. All right, so first of all, we need to talk about chemical reactions and what chemical reactions are, because chemical reactions pretty much are equivalent to a math equation. What do I mean by that? Well, in math, you have certain symbolism that you use to show relationships. So if I were to give you something like 2 + 3 = 5, at some point in your life, you were taught what those symbols mean. This symbol means you combine, okay? Plus means they go together. And this symbol means that those 2 sides are the same, okay? Equals means they're the same. And when you use that plus sign and you're combining things, it means you're putting them together to form something new. Okay, so in this case, you're forming, hold on, I gotta admit a bunch of people. You're forming a new number. But the point is, even though the number on the right of the equal sign looks different than what's on the left, they are actually equal to each other. Okay, and in a chemical reaction, we're going to have the same thing happen. The things on the left side of our reaction are going to be equal to what is on the right, even though they might look a little bit different. All right, let me clear that. Okay, so before we get started with what we call balancing and what balancing is, we need to know the terminology that we use to talk about chemical equations or chemical reactions. So I'm going to pop down to the bottom here first, just so you can see what a chemical reaction looks like. And we also call these chemical equations because, in fact, they are a lot like math equations. You will see that there is a plus sign. Okay, so you're going to see plus signs in chemical equations. You're also going to see an arrow. The arrow is equivalent to the equal sign. So even though we draw an arrow, what that really is an equal sign. So in a chemical reaction, the pieces on the left have to equal the pieces on the right. So just like any other equation, those 2 things are going to be equal. And we have to come up with different ways to make sure they are equal. We also give names to the stuff that's on the left side of the arrow and the stuff that's on the right side of the arrow. So On the left side, anything that is to the left of the arrow is called a reactant. And it's because those things are going to react with each other to produce the stuff that's on the right side of the arrow. Okay, so anything on the left side is called a reactant, and anything on the right side of the arrow is called a product. You might have one product, you might have 2, 3, 4, 5 products. And they're called products because they're being produced or formed. I'm sure you've seen chemical reactions before, you just maybe didn't know they were chemical reactions. So for example, if you've ever seen vinegar and baking soda mixed together, it gets nice and bubbly and frothy and kind of looks like a volcano. That's what a volcano reaction is when they do those models. You are taking 2 different reactants, vinegar and baking soda. You're mixing them up, you're combining them. That's what that plus sign represents. And then the arrow shows you that you are forming something new. And in the case of the baking soda and vinegar, it's actually forming a gas called carbonic acid. Okay, so that's all that a chemical reaction is. You're taking 2 things, you're changing them to form something else. But in the math of all this, everything still needs to be equal numerically. So what do I mean by that? So when we do a chemical reaction, when we take chemicals and we combine them, they're going to produce something new, but you cannot lose or gain matter in the process, meaning you simply can't have atoms disappear and you can't have atoms appear from nowhere. So the law of conservation of mass, also known as the law of conservation of matter, states that matter can't be created or destroyed in a chemical reaction. This means that the total number of atoms or molecules or moles, whatever quantity you're referring to, whatever you start with on the reactant side, means that same number have to appear on the product side. They might change from being an element to a compound or a compound into an element, but either way, the numbers have to be the same. Sometimes the numbers don't work out when a chemical reaction is first written. So we have to do something called balancing to get the math to be equal on both sides of the equation. So for example, let's take a look at this chemical equation or chemical reaction that I have at the bottom of the page. You're going to notice some things that look similar to what we've been doing, and then you're going to notice some things that we haven't seen before. So first of all, I'm going to rewrite this the way the original chemical reaction looked. So essentially what we did in this chemical reaction, if we were to do this in a lab, was we would have taken solid iron, so the element iron, we would have combined it with oxygen gas. And when we mix those 2 together, we end up with something called iron 3 oxide. Okay, we'll talk about the words later. But this is the basics of the reaction. We're taking iron and oxygen, we're putting them together, and we're forming this compound. We'll learn how to write these later. Right now, we just need to worry about balancing them. If you look at this reaction as written, though, the numbers game doesn't work out, meaning the reactant side and product side are not equal. If we look at the iron on the left side, the reactant side, there is only 1 iron atom there. Okay, because remember, if no subscript is written, it's a 1. So there's 1 iron on this side. But remember, this arrow is really just an equal sign. So if I have one iron on the left side of the arrow, I have to have one iron on the right side of the arrow. But here, this subscript 2 tells me that there's actually 2 irons on the right side. Those aren't equal. And if we look at the oxygens, we have the same problem. There's 2 oxygens on this side, and this 3 tells me there's 3 oxygens on this side. Well, those aren't equal. But this law of conservation of matter tells us that they must be equal. So this is where we have to do a little bit of work ourselves. We have to do what's called balancing the chemical equation. We need to somehow get the irons equal and the oxygens equal. And we do this using something called a coefficient. I'll show that term on the next slide. But what a coefficient is it is a number that you add in front of an element or compound symbol, so a full-size number, not a little one like a subscript, that allows us to multiply our numbers of atoms by that number to get the numbers to equal out. Now, I'm not going to go through this example because it's complicated. We're going to start with something more basic. But essentially, by putting those numbers in front, we're increasing the number of total atoms that we have. So the easiest way to do this is just to kind of work through an example and show you how we balance an equation. All right, so I've taken a basic reaction here, H2 plus O2, and then this arrow, and we're forming water. So we're taking hydrogen and oxygen and forming water. I have added lines here because this is going to help you remember where we can add numbers to balance equations. The numbers that go on these lines are going to make sure that this is in fact, truly an equal sign. Okay, so our hydrogen numbers have to be equal and our oxygen numbers have to be equal. So to keep track of your numbers, I suggest you create some kind of a chart so that you can keep track of what you're doing, because a lot of times you're going to have to bounce back and forth. And you'll see as we practice these what I mean. I recommend making a T-chart, and I created one here in the bottom right-hand corner for you. All this T-chart does is it keeps track of how many hydrogens we have on the reactant side versus the product side, and how many oxygens we have. So you start out by making a T. We're going to label the left side reactants and the right side products, because remember, the left side of the arrow is the reactants and the right side of the arrow is the products. Down the side, we just list the elements that are in our reaction. So you look for your element symbols and you write them. So we only have hydrogen and oxygen, and those should appear on both sides. So we have a hydrogen and we have oxygen. And now it's just a matter of counting. So you're going to balance one element at a time. So we're going to start with hydrogen and we're going to work until it's balanced, and then we're going to move to our next atom. So if we look at hydrogen and we go to the reactant side, which is over here, you will see that next to the H in the corner, there's a 2. So that means we have 2 hydrogens over on the reactant side. Now we go to the product side. And even though hydrogen is part of a compound now, we can still see that within this compound, there are 2 hydrogens. So this is great. That means our hydrogen is already what we call balanced, meaning this equal sign is true. There are 2 on the left and there are 2 on the right. So they are in fact equal. So as of right now, we don't have to change anything that relates to our hydrogen. But Not only the hydrogen has to be balanced, but also the oxygen. So let's check the oxygen. On the reactant side, there are 2 oxygens. On the product side, however, this O, remember that when there's no subscript written, we assume it's a 1. There is only 1 oxygen in the product. And that's not okay because they are not equal. So our goal here is now to make them equal. The only way to make them equal is by adding coefficients or big numbers in front of the element or compound symbols. This is very important. You never, ever, ever add or change subscripts. So what I mean by that is this chemical equation is already written and it is correct in terms of the way these formulas are written. I could not simply say, okay, well, I'm just going to change that subscript to a 2. And now look, they're equal. You cannot change your subscripts. Okay, so that is not an option. The only thing you can do to change your numbers of atoms is add a number in front. And that number then gets multiplied by the subscript to tell you how many you have. So since we have 1 oxygen here and we need 2, we would put a 2 in front of that entire compound. Notice I did not put the 2 in the middle, okay? Because hydrogen or H2O does not have a plus sign in the middle. It is a compound, and the 2 must go in front of the entire compound, okay? You can't break it up in the middle. So great, let's look at what that did to the oxygen. This 2 now gets multiplied by how many oxygens we had, which is 1. And that means we have 2 oxygens now. So we can cross out that 1 and put a 2 there. Wonderful, 2 and 2, that means our oxygens are balanced. But does anyone see a problem that we've created? What happened when we put that 2 in front of the water? What did we change? Isabella, do you know? The what? We changed the chemical. What else is in that chemical other than oxygen? You don't know? What else is in water other than oxygen? Hydrogen. So when we put that 2 in front of water, we didn't just increase the number of oxygens in our product, we also affected the number of hydrogens. So when the coefficient is put in front, it affects anything within that same compound. So what we've now done is we've actually changed the total number of hydrogens in our product side. We no longer have 2, but we have 4. Okay, so by fixing our oxygen, we've actually now screwed up our hydrogen. So we have to go back and rebalance the hydrogen. But we can do that because now we have 4 on the product side and only 2 on the reactant side. So let's see how we can fix that. If we go back to the reactant side, we need to turn that into 4. So what can we do to change that hydrogen into 4 without changing the subscript? Grace, what do you think? How can we change that into 4 on the left side? Two to which one? Okay, let's do what you said. So if we put a 2 here and a 2 here, that now changed our oxygen to 4, and we only have 2 on the right side. So do we need the 2 in front of the oxygen? No. Okay, all we're trying to fix here is the hydrogen. So all we do is put a 2 in front of the hydrogen, and that gives us those 4 hydrogens. Okay, I'm going to clear this a second because it's gotten kind of sloppy. Okay, so at this point, we have 4 hydrogens on the left. We have 4 hydrogens on the right. We have 2 oxygens on the left, and we have 2 oxygens on the right. So we have taken care of making sure everything is equal. Now you'll notice there is still a blank line. Normally, that's fine. You can leave the line blank because you don't have to add a coefficient there. But because a lot of the work we're going to do is in Classkick, and it's going to require you to put something in the box, whenever you don't need a 2, a 3, or 4, or a different coefficient, I want you to type a 1 into the box because the 1 doesn't change the value. It's still 2, but it gives us a number to put on that line. So every line needs a number, whether it's a 1 or something else. Okay, the next slide just shows that done in its final form. Okay, I'm going to give you another pretty simple one here to practice just to make sure you're understanding how we do this. So please try this one on your own. Okay, so I'm going to draw lines where your coefficients could go. That's my arrow. Okay, remember you want to set up a T-chart, so I'll help you set that up. You're going to have your reactant side, your product side. Okay, this line essentially is your arrow that separates them. The only elements we have are sodium and chlorine. If it helps you to draw lines to make it look more like a table, you can do that. Okay, so start by counting your sodiums on both sides, seeing if they're equal, and go from there. Okay, let's just work through this process together. We'll get plenty more practice then. Okay, so start with your first element, whichever one you want to choose. I'll give you some tips later about the best ones to start with, but this one you can start with either one. Okay, so if we look at our sodium, on the reactant side, there's 1, and on the product side, there's 1. So those are balanced. Next, we move to our chlorine. On the reactant side, there's 2, and on the product side, there's only 1. Okay, so we need more chlorines on the product side. We need to get to 2. So you take a coefficient and multiply it by your subscript. Now remember, that subscript is 1. So to get to 2, we would have to put a 2 in front of that entire compound. So that fixes the chlorine. We now have 2 chlorines on the right, 2 chlorines on the left. But because I put that 2 and it went in front of this compound that also has sodium in it, we have to now go back and change how that changed the sodium. So now we actually have 2 sodiums on the product side. And you'll see we still only have 1 on the reactant side. Well, we need to turn that 1 into a 2. The only thing we can do is multiply by a coefficient. So we're going to put a 2 in front of that. So that gives us 2 sodiums. And we're balanced. Again, fill in any empty lines with 1s, and that would be correct. So 2 sodium, 2 chlorine, 2 chlorine. Now, something that sometimes confuses students, this plus sign, anytime you see a plus sign, it breaks things apart. So meaning these sodiums and chlorines are not combined like they are on the right side. This is an element, this is an element. Here, we've combined them, there's no plus sign in between, so that is a compound, which is why the 2 in front of the sodium here does not affect this chlorine, but the 2 in front of this does affect both of these. Okay, so if you have a plus sign, it splits those and it allows them to be counted separately. Okay, now we're going to get into some specific examples that basically are just going to give you some tips and tricks to balancing some of the harder reactions, okay? Because not all reactions are only going to have 2 elements. Sometimes they're going to have 3, 4, 5, even 6 elements. So these tips are just to make your life easier, okay? You can balance any of these without the tips, but you're going to make it really hard for yourself. So please make sure you're noting these tips somewhere so that when you go to do them on your own, they're a little bit easier. Okay, so you can see this already looks a lot more complicated. You can see we have 2 reactants separated by a plus sign. We have 2 products separated by a plus sign. And we have 3 different elements here. So there's actually 2 tips combined here in this one example, okay? So my first tip is if you have any elements that appear more than once on the same side of the arrow. So for example, here's my arrow. Here's my arrow. I am looking for an element that appears more than once on the same side. Well, on the left side, carbon only appears once, hydrogen only appears once, oxygen only appears once. So nothing weird there. But if you look on the right side, you'll see that carbon only appears once, hydrogen only appears once, but look, oxygen appears in 2 places. Those are often harder to balance. So I save those for last. So if you see something that appears more than once on one side of the arrow, balance it last. So you'll see I put oxygen last in my list here. Additionally, this particular type of reaction we're going to learn later on is called a combustion reaction. Don't worry about that now, but in a combustion reaction, the elements are carbon, hydrogen, and oxygen. Those 3 elements should kind of ring a bell in your brain because those were also the 3 big elements when you were doing biology. I don't know if you remember, but when I taught biology, when we were talking about carbohydrates, lipids, proteins, etc., the saying I gave my kids was CHO, CHO, CHON, and CHONT. CHO, CHO, CHON, CHONT. The very first part of that, CHO, is carbon, hydrogen, and oxygen. And the reason I bring that up is because when you have those 3 elements, carbon, hydrogen, and oxygen, that's the order you should balance them in. So if those are your 3 elements, balance them in that order. CHO, carbon, hydrogen, and then oxygen. These are nearly impossible to balance unless you do them in that order. But if you do them in this order, they're really not bad. Okay, so carbon, hydrogen, and oxygen, we're going to balance them in that order. We set up our T chart. We've got our reactants, our products, our T, and then carbon, hydrogen, oxygen listed. I'm just going to add lines here so that it's easier to keep track of our numbers. All right, so now it's just the same process that we did before. We go to carbon, we look on the reactant side, the left side of the arrow. I'm just going to draw a line here. And there are 5 carbons because that 5 tells me there's 5 carbons. I go to the right side of the arrow and I see that there is only 1 carbon over here. Remember that that has an assumed subscript of 1. So right away, we have a problem. They are not equal. So we need to make them equal. Well, my 5 is bigger than my 1. So that means we need a coefficient on the right side. And in order to get 5 carbons, we're going to put a 5 in front of CO2. So that has fixed my carbons. I now have 5 on both sides. Let's see. I'm going to start calling on some of you to make sure you're paying attention. Let's see. Jason, you're my lucky first contestant. Jason, how many hydrogens are on my reactant side of the problem?
12.
12, good. So here's my reactants. Here's my 12 hydrogens. I'm going to make my window bigger here. Bobby, as it is written right now, before we do any balancing, how many hydrogens are on the right side of the arrow, the product side?
2.
2, good, because we have our 2 hydrogens right here. Bobby, again, how can we fix that? How can we get those 2 to be equal if we have 12 on the left and 2 on the right?
Multiply by 6.
Okay, which one? Where are we going to put the 6?
On the right. Next
On
to
the right in front of
the hydrogen.
not just the hydrogen, but the whole water. Okay,
Yeah.
so the 6 goes in front of the water. And now remember that that coefficient gets multiplied by the subscript, and that now gives us our 12 hydrogens. Now that 6 also affected the oxygen, but we haven't even looked at oxygen yet. So we don't even have to worry about that because we're going to figure that out now. Okay, so now let's look at our oxygen. So Annie, on the left side of the arrow, the reactant side, how many oxygens are there right now? 2, good. Okay, because it's just these 2 right here. When we look at the product side, this gets a little bit harder because remember that we have oxygen in 2 places. We have to count the total number of oxygens on that side. So any coefficients that have been written, we have to account for, and we have to look at what's already there. So this first oxygen, there are 2 of them here in CO2, but because we added that 5 in front already, we have to multiply that. So 5 times 2 means that there's actually 10 oxygens in that portion of the product. But there's also oxygen here. Remember, there's a 1 after that, but we have to multiply that by 6. So there are 6 oxygens on this product. So in total, this plus sign means that we have 10 oxygens plus 6 oxygens. So there are 16 oxygens on our product side. Lucky for us, oxygen only appears once on the reactant side. So if there were originally 2, but we need that to match 16, Gabe, what would we have to do on the product side to make those oxygens equal? Good. Good. So because we had 2, we need to multiply by 8. The only way we can change at this point is by putting that 8 in front. and that has now changed the oxygen to 16. When we put that 8 there, that does not affect our carbon and hydrogen, because remember, that's split up by that plus sign. So that only applies to that oxygen. I strongly suggest on ones like this, especially, that you go back then and double check when you finish to make sure everything is balanced.